Everything you were taught about how reality works, the atoms, the forces, the laws of physics, all of it is built on a foundation that physicists themselves cannot explain. Not the edges, the foundation. And the alarming part is not that one thing is missing. It is that when you pull at any layer of reality, any single thing physics claims to understand, you find another layer underneath that nobody has ever explained. 17 of them. Confirmed by experiment. Open for decades, some for 100 years. What is matter actually made of at the deepest level? Why does time only move one way? Does anything exist when nobody is looking at it? Is the universe we see actually real, or a projection of something we cannot access? These are not philosophical questions. Physicists have run the experiments. The data is in, and the answers are genuinely alarming. That is what this video is. All 17 layers. In order. Getting stranger every time. Something is holding the universe together that we cannot see, cannot touch, and after 90 years of trying, cannot find. And the first person who noticed this was laughed out of the room. His name was Fritz Zwicky. In 1933, he was studying a massive collection of galaxies called the Coma Cluster, roughly 1,000 galaxies pulled together by gravity into one enormous system. He wanted to know how fast they were moving. So he measured. And when the numbers came back, they did not make sense. The galaxies at the edges of the cluster were moving so fast that gravity alone should not be able to hold them in. Based on all the visible mass, every star, every gas cloud, everything the telescopes could pick up, the cluster should have been flying apart millions of years ago. But it was not flying apart. It was perfectly stable. So where was the missing mass? Zwicky proposed something radical. He said there must be matter out there that produces gravity but produces no light. Matter that is invisible by definition. He called it dunkel materie, dark matter. His colleagues ignored him for 4 decades. Then, in the 1970s, an astronomer named Vera Rubin measured the rotation curves of individual galaxies and found the exact same problem. Galaxies were spinning in ways that only made sense if most of their mass was invisible. The math was unambiguous. Something was there. Something enormous. Something that makes up about 27% of everything in the universe. And here is what I think gets lost in that number. 27% is not a rounding error. It is not a footnote. It is more than 6 times the mass of everything we have ever seen, touched, built a telescope to look at, or written a physics equation to describe. 6 times. And we have no idea what it is. What does it mean for a science to officially include something in its model that it cannot describe? And if the answer to that question does not sit comfortably with you, it should not. But what if the problem is not just that we cannot see it, but that every tool we have built to find it has come back empty? The search for dark matter is one of the most expensive, most coordinated, and most sustained experimental efforts in the history of science, and it has found nothing. To understand what that silence actually means, you have to understand what these experiments are. The detectors built to find dark matter are not simple devices. Xenon 1T, built under a mountain in Italy, used 10 tons of liquid xenon, cooled to minus 95 degrees, and surrounded by water shielding to block every known particle that might create false signals. Lakes in South Dakota sat nearly a mile underground inside an old gold mine. Pandex in China went even deeper. The entire point of burying these machines is to eliminate noise, to create the quietest possible environment so that if a dark matter particle passes through and nudges a single atom, the detector catches it. They have been running for decades, combined. Not one confirmed signal. Now, here is the question that physicists do not always phrase directly. What does 40 years of silence tell us? There are 3 possibilities and none of them are comfortable. The first is that dark matter exists, but interacts with normal matter so weakly that even our most sensitive detectors cannot catch it. The second is that dark matter exists, but is not made of the kind of particle we have been looking for, meaning decades of experiments were built on the wrong assumption. The third is something else entirely, something that most physicists are reluctant to say in public. Maybe the way we model gravity is wrong, and dark matter is not a thing at all, but a sign that our understanding of gravity breaks down at galactic scales. I find the third option the most unsettling. Not because it is necessarily right, but because it means the problem might be inside the theory we are using to look, not outside in the universe we are looking at. A tool that cannot find what it is looking for is either broken or looking in the wrong place. After 40 years, we have not figured out which one it is. This brings us to something even larger, because dark matter is only 27% of the missing picture. In 1998, 3 teams of astronomers were doing something that sounded straightforward. They were measuring how fast the universe was expanding by looking at a specific type of exploding star, a type 1a supernova, which always explodes with the same brightness, making it a reliable measuring stick across cosmic distances. The assumption going in was simple. The expansion of the universe, started by the Big Bang, should be slowing down. Gravity pulls things together. Of course it was slowing down. It was not slowing down. It was speeding up. Saul Perlmutter, Brian Schmidt, and Adam Rees, working in competing groups, all got the same result independently. The universe is not just expanding, it is accelerating. Something is pushing everything apart, and that push is getting stronger over time. They called it dark energy. They won the Nobel Prize in 2011, and then physics ran into a wall. Because here is what the theory says dark energy should be. In quantum mechanics, empty space is not actually empty. It seethes with tiny fluctuations of energy, particles popping in and out of existence. Theoretically, all of that vacuum energy should contribute to the push that is accelerating the universe. When physicists calculated how much energy empty space should contain, they got a number. When they measured how much dark energy is actually out there, they got another number. The two numbers disagreed by a factor of 10 to the power of 120. Let that sit for a moment. 120 orders of magnitude. That is not a calculation error. That is not a rounding issue. That is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science, by an almost incomprehensible margin. And yet the theory that produced this number, quantum field theory, is the same theory that predicts the magnetic moment of the electron to 12 decimal places. The same framework, wildly precise in one place, catastrophically wrong in another. Most physicists will tell you this is a puzzle waiting to be solved. I think it is something more specific than that. It is a signal that something is structurally wrong with how we are connecting our two best theories of reality. There is a darker layer here. In April 2024, a collaboration of scientists released the most detailed map of the universe ever constructed. 6 million galaxies, 11 billion years of cosmic history plotted with a precision that no previous survey had approached. The project was called DESI, the Dark Energy Spectroscopic Instrument, and what it found quietly demolished a model that had stood unchallenged for 25 years. The standard model of cosmology, called lambda CDM, treated dark energy as a constant, a fixed number, a permanent feature of space that does not change. This assumption sat at the core of every cosmological calculation made since the late 1990s. It was not a tentative hypothesis. It was the foundation. DESI's data suggests the foundation is wrong. The measurements indicate that dark energy is not constant. It changes over time. It behaves more like a dynamic field, something that evolves, than a fixed property of empty space. The statistical confidence of this result sits at 3.9 sigma. In physics, 5 sigma is the threshold for a confirmed discovery. 3.9 is described as a strong hint. But a strong hint built on 6 million galaxies and 11 billion years of data is not the kind of thing you dismiss over breakfast. What does it mean if dark energy changes? It means lambda CDM, the model we use to describe the large-scale structure of the entire universe, is at minimum incomplete and at maximum wrong in a fundamental way. Every prediction made using that model, every calculation of how the universe evolved and where it is going, now sits on uncertain ground. And here is what I keep coming back to. This is not an anomaly from a single experiment. This is the universe itself, measured across billions of light years and billions of years of time, telling us something does not fit. We built the most precise map of reality we have ever made. And the map is showing us that the territory is different from what we thought. Ask yourself what it means to lose your model of the entire universe in a single dataset. To understand how deep this goes, we have to step back from the cosmos and look at what happens when physics tries to measure something much smaller, and finds that the act of measuring it changes everything. Planck was not trying to change physics. He was trying to stop an equation from producing something insane. Classical physics said that any hot object, a furnace, a candle, a human body, should radiate infinite energy. Infinite. Every object you have ever touched should, according to the physics of the time, be pumping limitless radiation into the universe. Obviously, nothing like that was happening. But the math kept insisting it should. So Planck added a patch. He said energy cannot flow continuously. It has to move in tiny fixed chunks. Little packets. He called them quanta. He later said this was an act of desperation. He did not believe the chunks were real. He thought he had found a trick to make the equation behave. The trick was real. Within 25 years, experiment after experiment confirmed it. Energy genuinely moves in packets. The universe actually works that way at its smallest level. Planck's desperate fix was not a fix. It was the first true glimpse of how nature is built. And here is the part that does not get said enough. The man who discovered quantum mechanics did not believe in quantum mechanics. He was right about the math and completely wrong about what the math meant. So ask yourself, if the person who wrote the equation did not understand what it was describing, what does that say about every equation being written right now? Ask yourself how many of our current fixes are real and how many are just patches that happen to work. And ask yourself whether there is actually a difference. And I think this is a warning, not a footnote, because what came next was a method that works perfectly, and that nobody has ever fully understood why it works. But what if the most accurate tool in the history of science is built on something we have been deliberately not looking at too closely? Here is the most accurate prediction in the history of science. Physicists calculated that a property of the electron, how it responds to a magnetic field, and the number they got matched the measured value to 12 decimal places. 12. If you were measuring the distance from New York to Los Angeles, that accuracy would put you within the width of a human hair. Physics did that. Now here is the part that should bother you. The method that produced that number works by running into infinity and cancelling it out by hand. When you calculate how an electron interacts with its own field, the math produces infinite values, numbers that mean nothing. So physicists developed a procedure. They subtract one infinity from another, extract a finite answer, and move on. Richard Feynman, one of the people who built this method, called it sweeping things under the rug. His words. The man who built the tool described it as hiding something rather than solving it. So what is under the rug? We do not know. We have the right answer. We have a procedure that produces it. We do not have a full understanding of why the procedure works. And everything in modern physics, every particle experiment ever run, every calculation that predicted the behavior of matter, sits on top of this method. Ask yourself what you call a foundation that works perfectly and is not understood. Ask yourself whether getting the right answer is the same thing as understanding why the answer is right. And ask yourself what happens to everything built on top of this if we ever have to look under the rug and find something we cannot cancel out. Most physicists will tell you this is a solved problem, just technically messy. I think that is the most comfortable version of the story. The less comfortable version is that we built the most precise science in history on a method its own architects admitted they could not fully explain. But what if the problem goes deeper, into the moment when physics actually happens, and finds it has nothing to say? Physics cannot explain the moment when physics happens. Let that land. Every experiment in quantum mechanics ends the same way. You set up a system. The math describes it as existing in multiple states simultaneously. The particle is here and there and everywhere the probability allows. Then you measure it. And it is somewhere specific. One place, one outcome. The wave of possibilities collapsed into a single fact. The Schrödinger equation, the equation that governs all of this, does not contain the moment when that collapse happens. There is no term for it. No variable that switches on when a measurement occurs. The equation describes the wave of possibilities evolving smoothly through time. And then reality produces one outcome. And the equation has nothing to say about how or why that transition occurs. This is not a philosophical gap. It is a technical hole in the center of physics. The most common event in the universe, a quantum system interacting with anything large enough to count as a measurement, is something the theory cannot describe. 100 years. No equation for it. Ask yourself what kind of science that is. You build an experiment. You get a result. The mathematical framework you use to understand that result cannot tell you how the result came to exist. It gives you the probability of each possible outcome. It cannot tell you why this one and not the others. Ask yourself what the word understand means if it stops exactly at the moment you actually need it. And I think this is the part nobody says out loud at conferences. Not because it is a secret, because it is uncomfortable. Because the theory works so well everywhere else that admitting this hole feels like it should matter more than it does. But the hole is there. And it has been there since the 1920s. To understand what this looks like in practice, we have to look at an experiment from 1922 that showed reality making a choice and refusing to explain itself. In 1922, two physicists named Otto Stern and Walter Gerlach fired silver atoms through a magnetic field. What they saw should not have been possible. Classical physics said the atoms would spread out into a continuous smear. A magnetic field should deflect atoms by varying amounts depending on their orientation. And since orientations are continuous, pointing in any direction, the result should be a smooth gradient across the detector. That is what classical physics predicted. That is what everyone expected. Instead, the atoms landed in two distinct spots. Two. Nothing in between. The atoms were not deflected by varying amounts. They were deflected by exactly one of two fixed values, as if reality had looked at the continuous range of possibilities and decided, no, only these two. Pick one. This was the experimental discovery of quantum spin, and it meant something that physicists have been living with uncomfortably ever since. Reality is not continuous. At the fundamental level, certain properties of matter do not come in smooth gradations. They come in steps, fixed values, discrete chunks, and when a particle is forced to choose, it chooses instantly without intermediate states, and lands exactly where the quantum rules say it should land, with exactly the probability the math predicts. The math works, every time, with extraordinary precision. But here is the question that the math does not answer. Why does the universe come in steps? What is the physical reason that a silver atom cannot have a spin pointing in any arbitrary direction, that it must choose between exactly two options and nothing else? We can write down the rule, we can calculate the probabilities, we cannot tell you why the rule is the rule. And here is what I find genuinely strange about this. We discovered that reality is quantized, that it comes in discrete chunks as a surprise. It was not predicted. It was not derived from first principles. It was found by accident when an experiment produced a result that had no business existing. The universe handed us a fundamental fact about its own structure, and we had no framework to understand why it is true. We have been using that fact to build technology for 100 years. We still do not know why it is true. This brings us to what happens when you follow that question long enough and realize that physics has not made a genuinely new fundamental discovery in over a decade. They found the last piece. The machine kept running, and then nothing. In 2012, CERN announced the Higgs boson, the final particle predicted by the Standard Model, the one that had been missing for 50 years. Peter Higgs sat in the auditorium and wiped his eyes. It was supposed to be the beginning of what comes next. A door opening into new physics. The door did not open. The Higgs boson was exactly where the Standard Model said it would be. Exactly the mass the model predicted. No surprises, no anomalies, no cracks in the theory where something new was hiding. And that, of all things, was the problem. Because the Standard Model is not a complete theory. Every physicist knows this. It leaves out gravity. It cannot explain dark matter. It has no idea why there is more matter than antimatter in the universe. It is, in the words of the people who use it daily, a placeholder, a framework that works brilliantly within its limits and collapses outside them. The LHC was built to find what lies beyond those limits. It was designed to reach the energies where something new had to appear. Almost every theoretical prediction said so. It has been running since 2008. It found the Higgs. It found nothing else. And here is what I keep coming back to. The silence after 2012 is more significant than the discovery that came before it. A discovery tells you where you are. Silence tells you that where you thought you were going does not exist. The most expensive scientific instrument ever built confirmed what we already knew, and gave us nothing to build on. Ask yourself what that silence means for the next generation of physicists. Ask yourself what a field does when its primary tool stops producing new results. And ask yourself whether this is a temporary plateau or the first sign of something more permanent. But what if the silence is not random, but the result of a specific bet the field made and lost completely? Imagine spending 40 years on a theory. Not alone. Thousands of physicists. Hundreds of thousands of papers. Entire careers. Graduate students trained to work inside it. And then the machine designed to confirm it runs for years and finds nothing. That is supersymmetry. And that is exactly what happened. The idea was elegant. Every particle we know has a partner, a heavier mirror version with slightly different properties. The electron has the selectron, the quark has the squark. These partners were predicted to be heavy enough that we had not seen them yet, but at the energies the LHC would reach, they had to show up. It solved three problems at once: the hierarchy problem, dark matter, the unification of forces. It was too elegant to be wrong. That is exactly what physicists said. And that is exactly what they said before the results came back empty. No superpartners. At any mass. At any energy the LHC could reach. So ask yourself what happens to a field when its dominant framework, the one that shaped careers, grants, curricula, entire research programs for 4 decades, leaves no trace in the machine built to find it. Ask yourself what happens to the intuition of a generation of physicists who spent their best years looking in a direction that turned out to be empty. And ask yourself whether the problem is that supersymmetry is wrong, or that we have no idea what to look at next. And I think this is the part that does not get said directly enough. When you lose your most promising direction, you do not just lose a theory, you lose the map. You are still in the same territory. You just no longer know which way is forward. There is a darker layer here. Pick up a paperclip. Hold it between 2 fingers. Now take a small magnet and hold it an inch away. The paperclip moves toward the magnet. You just watched electromagnetism defeat gravity across a distance. The electromagnetic force of a magnet smaller than your thumbnail overpowered the gravitational pull of an entire planet. That gap between electromagnetism and gravity is not a small difference. It is 38 orders of magnitude. Gravity is 10 to the power of 38 times weaker than electromagnetism. Written out, that number has 38 zeros after the 1. It is, by any measure, the most extreme disproportion between two fundamental forces in nature, and physics has no explanation for why. This is called the hierarchy problem. It is not a new puzzle. It has been sitting at the center of theoretical physics since the 1970s. The Standard Model contains no mechanism that would naturally produce such an enormous gap. In fact, when you calculate corrections to the Higgs mass using quantum field theory, you get contributions that should push the mass up to the highest energy scales in physics, far larger than what is observed. To get the Higgs mass we actually measure, those contributions have to cancel each other with a precision of 1 part in 10 to the 34th, 34 decimal places of accidental cancellation. That is not a coincidence. Coincidences at that scale do not exist. What this means is that the Standard Model, as it stands, requires a kind of fine-tuning that no known physical principle can account for. The numbers work only if they are set with extraordinary precision by something the theory does not contain. Supersymmetry was supposed to solve this. Its mathematical structure would have made the cancellation natural rather than accidental. Without it, the problem remains completely open. Ask yourself what it means for a theory to require its own numbers to be set by hand to 34 decimal places. And then ask yourself how much you trust a foundation that is built on an accident that large. And here is what I keep returning to. The hierarchy problem is not discussed much outside physics. It does not make headlines, but it means that the theory governing every particle interaction ever measured contains, at its core, a number that has no explanation. We are not missing a detail. We are missing something structural. To understand why, we have to look at the moment when one physicist decided to say this out loud, and what happened when he did. In 2006, a physicist published a book saying his own field had stopped working. Not a critic from outside, someone who had spent decades inside it, and the response told you everything about where physics actually was. Lee Smolin's book was called The Trouble with Physics. The argument was simple. For 30 years, string theory had dominated theoretical physics. Thousands of careers, billions in funding, and it had produced 0 testable predictions. Not approximately 0, exactly 0. You could not design an experiment that string theory said would come out one way and not another. It had no contact with reality. And the community had decided that was acceptable because the mathematics was beautiful. Smolin was not a crank. He co-founded Loop Quantum Gravity, a serious competing approach. He knew the people he was writing about, and what he described was not stupidity. It was something more uncomfortable. A culture where young physicists who wanted jobs worked on string theory because that was where the positions were. Where alternatives were not encouraged. Where beauty had replaced testability as the standard for a good theory. The response from the physics community was intense. But here is what struck me about it. Critics rarely argued that string theory had made predictions that were confirmed. They argued that the mathematics was too deep to abandon. That elegance was its own justification. And I think that is the moment physics stopped being science and started being faith. Beautiful math. No contact with reality. A community that decided that was acceptable. That is not how we built everything else that works. Ask yourself what a theory owes us if it cannot be wrong. Ask yourself whether elegance has ever built a bridge or cured anything. And ask yourself why the most important conversation in physics is one most people outside it have never heard of. But what if the problem is not just the theory, but how deep the layers go underneath it? Every time physics found the smallest thing, it turned out not to be the smallest thing. This has happened so many times that at some point you have to ask whether it is a pattern, and what the pattern means. In the 1800s, atoms were the answer. The word itself comes from the Greek for indivisible. Chemists had traced matter down to its fundamental units and found something that could not be cut further. The atom was the flaw. Then, in 1897, J.J. Thomson fired electricity through a glass tube and found something smaller, the electron. The atom had parts. The flaw had a basement. By the early 1900s, Rutherford had found the nucleus at the atom's center. By the 1930s, the nucleus had been broken into protons and neutrons. Each new layer was announced as fundamental, as the thing from which everything else was built. Each turned out to have structure underneath. Then, in the 1960s, Murray Gell-Mann proposed that protons and neutrons were not fundamental either. They were made of quarks, smaller particles bound together so tightly that they have never been observed individually. Pull a quark out of a proton, and the energy required creates new quarks before the original one can be isolated. The flaw kept moving down. So where does it end? String theory, which we will come to properly later, proposes that quarks and electrons are themselves not fundamental. They are, according to the theory, tiny vibrating loops of energy called strings, operating at a scale so small that no instrument we could conceivably build would ever see one directly. The Planck length, the scale at which string theory operates, is to a proton what a proton is to the solar system. And here is what I think is the honest version of where this leaves us. We do not know if the regression stops. We have no physical principle that says reality must have a bottom layer. We have assumed at each stage that we had reached it. We have been wrong every single time. And the framework that currently proposes the deepest layer, strings, cannot be tested. What does it mean to build a picture of reality on a foundation that may itself have no foundation? There is a darker layer here. Most people think of space as the container that everything sits inside. The empty stage, the blank backdrop. It feels obvious. It is probably wrong. If you take quantum mechanics seriously, and we have to, because it keeps being right, then space itself should be quantized. If energy comes in minimum packets, if spin comes in fixed values, if everything at the quantum level is discrete rather than continuous, then space cannot be the exception. There should be a smallest possible distance, a minimum unit of space below which the concept of location stops meaning anything. That distance exists. We call it the Planck length. It is so small that a proton, which is already almost impossibly tiny, is as much larger than the Planck length as the solar system is larger than a proton. We cannot get anywhere near it. No instrument we could conceivably build would probe that scale directly. But here is what that means for the space you are sitting in right now. If loop quantum gravity is correct, and it is one of the most serious frameworks we have, then the smoothness of space is an illusion. What looks like a continuous, seamless geometry is actually granular, at a scale we cannot see. Like a photograph that looks smooth until you zoom in close enough to see the pixels, except we can never zoom in that far. So ask yourself what you are actually moving through when you move through space. Ask yourself what distance means if it breaks down below a certain scale. And ask yourself whether a universe with a minimum length is the universe you thought you were living in. And what I find most unsettling about this is not the idea itself. It is that we cannot check it. We derive the requirement from mathematics, confirm that it fits with what we know, and then hit the wall of our own instruments. The grain of space may be real. We may never see it. To understand why, we have to look at what happens when you try to build a theory around that grain, and end up with more universes than you can count. String theory is the most ambitious idea in the history of physics. It is also, depending on who you ask, either the most promising path to a complete theory of reality or the most sophisticated dead end ever constructed. The core idea is this: every particle, every electron, every quark, every photon is not a point object, but a tiny vibrating loop of energy. A string. Different particles are different vibrational modes of the same fundamental object, the way a guitar string can produce different notes depending on how it vibrates. This single idea, if correct, would unify all particles and all forces, including gravity, into one mathematical framework. It would be the complete theory of everything that physics has been searching for since Einstein. The mathematics of string theory is genuinely extraordinary. It is deep, internally consistent, and has produced insights that have transformed pure mathematics. Physicists who work in it describe an almost aesthetic pull. The sense that something this beautiful must be pointing at something real. Here is the problem. String theory requires space to have 10 dimensions, 9 of space and 1 of time. The extra 6 dimensions are curled up at scales too small to detect. And the way those dimensions curl up determines the specific physics of the universe, the masses of particles, the strengths of forces, the value of the cosmological constant. Different configurations of the extra dimensions produce different physics. How many configurations are possible? The current estimate is 10 to the power of 500. That is not a range. That is the number of distinct versions of physics that string theory mathematically permits. Each one describes a different universe with different laws. We live in one of them. We cannot calculate which one from first principles. We cannot test the others. We cannot even find a principle that would select our universe from the landscape of possibilities. Peter Woit, a mathematician at Columbia, has argued for years that a theory with this many solutions is not really making predictions at all. Leonard Susskind, one of the architects of string theory, has argued the opposite, that the landscape is not a failure, but a feature, a map of all possible physics, of which ours is one. The argument has been running for 2 decades. And here is my honest reading of where it stands. A theory that describes 10 to the 500 universes and cannot specify which one we live in has a problem that goes beyond experimental access. It is not that we cannot test it yet. It is that the framework may be too flexible to be wrong, and a theory that cannot be wrong cannot tell you anything definite about reality. But what if the problem is not the number of solutions, but something more fundamental about what we are trying to unify in the first place? At the center of every black hole, and at the first instant of the Big Bang, the 2 best theories in physics are required simultaneously. General relativity, which describes gravity, space and time, and quantum mechanics, which describes everything else at the smallest scales. Both theories are needed. Both theories work with extraordinary precision in their own domains. And when you try to apply them together, the mathematics produces nonsense, not approximate nonsense, not results that are slightly off, division by 0, infinite values with no physical meaning. The calculation breaks down completely. This is not a technical problem waiting for a better computer. It is a structural incompatibility. General relativity treats space and time as a smooth, continuous fabric that bends in the presence of mass. Quantum mechanics treats the world as fundamentally discrete and probabilistic, with fields that fluctuate randomly even in empty space. These 2 pictures of reality are not just different. They make contradictory assumptions about the nature of space itself. So ask yourself what it means that our 2 most successful theories, tested to extraordinary precision, used to build GPS satellites and MRI machines and particle accelerators, cannot exist in the same equation without producing gibberish. One of 2 things must be true. Either general relativity is not quite right at the smaller scales, or quantum mechanics is not quite right at the larger scales, or both are approximations of a deeper theory that we do not have yet. Every approach to quantum gravity, string theory, loop quantum gravity, causal dynamical triangulations, is an attempt to find that deeper theory. None of them has made a confirmed experimental prediction. And here is what I find most striking about this situation. We know exactly where the problem is. We know the precise conditions under which our 2 best theories fail. The center of a black hole. the first fraction of a second after the Big Bang. These are not vague unknowns. They are specific locations where the known laws of physics stop working. We have circled them on the map. We just cannot go there. And we cannot build a theory that describes what happens there without the math collapsing. What does it mean to know exactly where your understanding ends and have no clear path to what lies beyond it? To understand why, we have to step back and look at what happened when physics tried to resolve this incompatibility and found itself generating not one version of reality, but an uncountable number of them. Einstein put a number in his own equation that he did not believe in, threw it out when it became inconvenient, and 30 years later, the universe handed it back. He was right twice, for completely wrong reasons, and we still do not know what the number actually is. In 1917, his equations of general relativity kept producing a universe that was either expanding or collapsing. That was unacceptable. Everyone assumed the universe was static and eternal. So he added a term, a constant, something that acted like a repulsive force to hold everything in balance. He later called it the biggest blunder of his career. Then Hubble showed the universe was expanding. The constant was wrong. Einstein dropped it. Then, in 1998, the expansion turned out to be accelerating. Something was pushing everything apart with increasing force. Something that behaved exactly like a repulsive force built into the fabric of space. Lambda was back. The blunder was the answer. But here is what nobody says clearly enough. The cosmological constant works as a description. The number fits. What it does not do is explain itself. We do not know why space has this particular energy density. We do not know where the number comes from. We cannot derive it from anything deeper. It sits in the equation because the universe requires it, and the universe has not told us why. Ask yourself what it means to have the most important number in cosmology be one we cannot explain. Ask yourself what kind of science inserts a number by hand, confirms it experimentally, and calls that understanding. And ask yourself how many other numbers in our equations are in the same position, correct, confirmed, and completely unaccounted for. But what if the framework we use to test any explanation is itself built on assumptions nobody can verify? Every time you measure something in quantum mechanics, the universe splits. Every possible outcome happens. You end up in one branch. The others are just as real. This is not fringe. It is taught at serious universities. It is defended by serious physicists. And it cannot be tested. Ever. By construction, the other branches are inaccessible. There is no experiment that would confirm or rule out their existence. The interpretation is consistent with every piece of data ever collected, because it is consistent with every possible result. The man who proposed this was named Hugh Everett. He submitted it as his doctoral thesis at Princeton in 1957. His advisor was John Wheeler, one of the most important physicists of the century. The community received it poorly anyway. Everett left academia, went to work in defense, and died in 1982, largely ignored by the field he had tried to transform. He reportedly said history would vindicate him. He did not live to see it happen. And something genuinely strange has happened since. Many worlds is now mainstream. David Deutsch, one of the founders of quantum computing, says it is the only interpretation that takes the mathematics fully seriously. Physicists who dismissed it for 20 years now teach it to graduate students. Ask yourself what it means that the interpretation considered most serious by a significant fraction of physicists is one that cannot be tested in principle. Not because our instruments are not good enough, but because the math forbids it. Ask yourself what the word scientific means when applied to a framework that is consistent with every possible observation. And ask yourself what we are doing when we accept untestable parallel realities as a leading position in an experimental science. And I think this is where something quietly broke in physics. Not loudly, not with a press release, just a gradual acceptance that some questions cannot be answered, and a decision to keep working anyway. There is a darker layer here. Two of the most brilliant physicists of the last half-century spent 30 years arguing about what happens to information when it falls into a black hole. The argument was not resolved. It was declared over when one side changed its mind, and the reasons for that change are still debated. The problem begins with Stephen Hawking's 1974 discovery that black holes are not entirely black. Quantum effects near the event horizon, the boundary beyond which nothing can escape, cause black holes to slowly radiate energy and particles. This radiation, now called Hawking radiation, is thermal. It is random. It carries no information about what fell in. And because the black hole is losing energy through this radiation, it eventually evaporates completely. Here is the problem. Quantum mechanics has a rule, one of its deepest rules, that information cannot be destroyed. Every physical process is, in principle, reversible. If you know the final state of a system with perfect precision, you can calculate its initial state. This is called unitarity, and it is not optional. It is baked into the mathematical structure of quantum mechanics at a fundamental level. But if a black hole evaporates and the radiation carries no information about what fell in, then information has been destroyed. A star, a planet, a library. Everything that ever crossed the event horizon is gone. Not just inaccessible, gone. Unitarity is violated. So ask yourself which gives way: the structure of quantum mechanics or the structure of general relativity? Hawking said information was genuinely lost. Susskind said it could not be. Unitarity was inviolable. And the information had to escape somehow, encoded in the Hawking radiation in a form too subtle to see directly. They argued publicly for 3 decades. In 2004, Hawking conceded. He said he had been wrong and information was preserved. He did not provide a complete mechanism for how. And here is what I think the honest version of this story looks like. The argument ended, but the problem did not. We do not have a complete description of how information escapes a black hole. We have arguments that it must, based on unitarity, and we have the mathematics of the holographic principle pointing in a direction. But the actual mechanism, the physical story of how every piece of information that ever crossed an event horizon gets encoded in outgoing radiation, remains an open question. 30 years. 2 of the greatest minds in physics. The conclusion: information is probably preserved, we think, but we cannot fully show you how. To understand why, we have to look at the mathematical framework that emerged from this debate, and what it implies about the nature of space itself. In 1997, Juan Maldacena published a paper that is now the most cited in the history of theoretical physics. What it showed was that 2 completely different theories, one with gravity, one without, one in 5 dimensions, one in 4, are mathematically identical. Every calculation in one maps perfectly onto a calculation in the other. They are the same theory written in 2 different languages. The implication is something that sounds wrong the first time you hear it. The 3-dimensional interior of a space, everything inside it, every particle, every force, gravity itself, can be completely described by a theory living on its 2-dimensional surface, like a hologram. A flat film that contains all the information needed to reconstruct a 3-dimensional image. The universe might work exactly like that. Think about what that means for the room you're sitting in right now. The depth of it, the distance from where you are to the wall across from you, might not be fundamental. It might be a property that emerges from information encoded on a surface you cannot see, in fewer dimensions than you experience. The 3rd dimension might be something the universe generates, not something the universe is made of. Ask yourself how you would know the difference. Ask yourself what the word real means if the dimension you move through every day is emergent rather than fundamental. And ask yourself whether a physics that arrives at this conclusion by following the mathematics of black holes, not by looking for it, is telling us something about reality or something about mathematics. Most physicists say it is just a powerful calculational tool. I do not know what just means when the tool is exact, complete, and describes everything we observe. At some point, just math and reality become the same thing. And I think we pass that point without noticing. But what if the two theories that were supposed to describe all of this cannot coexist in the same equation without destroying each other? There are two rulebooks for reality. One describes everything large, planets, galaxies, the shape of space itself. The other describes everything small, atoms, particles, the behavior of energy at its most fundamental. Both rulebooks are right. Both have been tested more thoroughly than any other ideas in science, and they cannot both be true at the same time. General relativity says space is smooth. It bends, it stretches, it curves around mass like a rubber sheet under a heavy ball. The geometry is continuous. There are no gaps, no jumps, no minimum unit of distance. Quantum mechanics says the opposite. At the smallest scales, everything is granular. Energy comes in packets. Probabilities replace certainties. Fields fluctuate randomly, even in empty space. These are not just different descriptions. They are contradictory assumptions about what reality is made of. For most situations, this does not matter. General relativity handles the large. Quantum mechanics handles the small. They operate in separate domains and the contradiction stays quiet. But there are places where both are needed simultaneously. And in those places, the math stops working entirely. Not approximately. Not with small errors. It produces infinities, division by zero, numbers that mean nothing. So ask yourself what kind of foundation that is. We have built the entirety of modern physics on two frameworks that are individually perfect and mutually incompatible. Every physicist knows this. It is not a secret. It is the central, unsolved problem of the field. And what I find most striking is this. We have known about the incompatibility for nearly a century. We have not resolved it. We have learned to work around it, to use one theory here and the other there, and to avoid the places where they collide. But avoidance is not understanding. To understand what happens when you cannot avoid it anymore, we have to look at the specific place where the collision becomes impossible to ignore. In 2012, a physicist named Joseph Polchinski sat down with two colleagues and worked through the mathematics of what happens at the edge of a black hole. They were not expecting what they found. What the math produced was so uncomfortable that when they published it, the physics community spent years trying to find a mistake. Nobody found one. The problem starts with the event horizon, the boundary around a black hole beyond which nothing can escape. General relativity says crossing an event horizon should feel like nothing. No sudden wall, no dramatic moment. You would fall through it without noticing, at least for a while. The horizon is invisible. It is a point of no return defined by geometry, not by any physical structure. Polchinski's calculation said otherwise. When you apply the rules of quantum mechanics to the event horizon, specifically the rule that quantum information cannot be destroyed, the math produces a wall of intense radiation right at the boundary. Not inside, right at the edge. An observer falling in would not drift through gently. They would hit something. This is called the firewall paradox. And here is why it matters beyond black holes. The firewall is not a prediction that can be tested. We cannot send observers into black holes and ask what they experienced. It is a logical consequence. If quantum mechanics is right, and if general relativity is right, and if information is preserved, then a firewall must exist. But if a firewall exists, then general relativity is wrong about what crossing a horizon feels like. 3 assumptions, all considered solid. Together they produce a contradiction. What does it mean when your best theories corner each other like this? One of them has to bend. We do not know which one. And I think this is the honest picture of where theoretical physics stands right now. Not at the edge of completion, but at a 3-way contradiction with no clear exit. There is a darker layer here. Einstein did not like quantum mechanics. He used it. He understood it better than almost anyone. But he did not believe it was the final word on reality. In 1935, he published a paper with two colleagues, Boris Podolsky and Nathan Rosen, that he thought would demonstrate quantum mechanics was incomplete. The paper described a situation so strange that surely, he argued, something was missing from the theory. The setup is this. Two particles interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles, like their spin, remain connected even after separation. Measure one particle and you instantly know something about the other, no matter how far away it is. Einstein called this spooky action at a distance and said it was absurd. If measuring one particle instantly affects another particle on the other side of the room or the other side of the galaxy, then information is traveling faster than light, and nothing travels faster than light. Therefore, Einstein concluded, quantum mechanics must be incomplete. There must be hidden variables, additional information carried by the particles that determines the outcome of measurements in advance, without any need for instant connection across space. It was a clean argument. It felt airtight. Ask yourself, which is more disturbing, that Einstein was wrong, or what being wrong actually implied? Because the experiment he designed to show quantum mechanics was incomplete ended up doing the opposite. The mathematics of his argument was eventually turned into a testable prediction. And when it was tested, quantum mechanics won. The hidden variables do not exist. The instant connection is real. Einstein spent the last 20 years of his life convinced quantum mechanics was missing something. The missing something turned out to be in his own assumptions about how reality works. But what if the problem is not just the connection between particles, but what that connection reveals about whether reality exists at all before we look at it? In 1964, a physicist named John Bell did something quietly devastating. He took Einstein's argument about hidden variables and turned it into mathematics. He derived an inequality, a precise numerical limit, that any theory with hidden variables must satisfy. If the world works the way Einstein thought it did, with particles carrying predetermined answers to measurement questions, experiments would produce results within Bell's limit. If quantum mechanics was right, and the connection between particles was genuinely instantaneous and non-local, experiments would violate it. The experiments were run. The limit was violated. Alan Aspect and his team confirmed this in 1982 with precision that left no room for alternative explanations. The result has been confirmed hundreds of times since, with increasingly careful controls closing every possible loophole. The most recent loophole-free tests were completed in 2015. The answer has not changed. Reality is non-local. Two particles that have interacted remain connected across any distance. Measuring one instantly determines something about the other. This is not a metaphor. It is not an approximation. It is a measured, reproducible, experimentally confirmed property of the universe we live in. And here is what this actually means, stated plainly. Einstein's picture of reality, where objects have definite properties independent of measurement, and where nothing influences anything else faster than light, is wrong. Not approximately wrong. Ruled out by experiment. What does it mean that the most intuitive picture of reality, the one where things exist and have properties whether or not you look at them, has been experimentally eliminated? Most people walk through their lives with Einstein's picture of reality in their heads. Solid objects with definite properties connected to other objects only through forces that travel at finite speed. That picture is wrong. The universe does not work that way. And I think the fact that this is not the first thing we tell people about physics says something about how uncomfortable the truth actually is. To understand why, we have to look at what this non-locality means for the constants that make our existence possible, and why those constants look nothing like an accident. Fred Hoyle was an astronomer who did not believe in the Big Bang. He coined the term mockingly. He was wrong about that. But in 1953, he did something that remains one of the strangest moments in the history of science. He predicted a property of carbon not because the physics suggested it, but because we exist. The argument worked like this. Carbon is the foundation of life. Every living thing is built on carbon chemistry. For carbon to exist in the universe in the quantities we observe, it has to be produced inside stars through a specific nuclear reaction involving 3 helium nuclei colliding and fusing. Hoyle calculated that for this reaction to happen at the rate required to produce enough carbon, the carbon nucleus must have a very specific internal energy level, a resonance at almost exactly the right energy to make the reaction efficient. At the time, no such resonance had been measured. The nuclear physics data did not show it. Hoyle went to a laboratory at Caltech and told the experimenters to look for it, at a specific energy. They thought he was wasting their time. They looked anyway. It was there, exactly where he said. Hoyle reportedly walked out of the lab shaken. He had predicted a nuclear property of carbon, using only the fact that carbon-based life exists. The universe, it seemed, had been arranged so that carbon would form. He later wrote that this felt less like a discovery and more like reading a message. So ask yourself, what kind of universe produces exactly the nuclear resonance required for its own observers to exist? Is that a coincidence? And if it is not a coincidence, what is the alternative? This brings us to the question that makes physicists most uncomfortable, not because the science is unclear, but because the answer sits at the edge of what science can address. Change the strength of the strong nuclear force by 2%. Just 2. In one direction, protons cannot form. In the other direction, hydrogen burns too fast, and stars like the Sun do not exist long enough for planets to develop life. Either way, we are not here. Change the strength of electromagnetism slightly, and chemistry stops working. Change the ratio of the electron mass to the proton mass, and stable molecules become impossible. Adjust the cosmological constant upward by a factor of a few, and the universe expands so fast that matter never clumps into galaxies. Adjust it downward, and everything collapses back before stars can form. In 1973, physicist Brandon Carter gave a name to this pattern. He called it the anthropic principle. The basic observation is that the physical constants of our universe, the numbers that set the strengths of forces, the masses of particles, the rate of expansion, appear to be tuned with extraordinary precision to permit the existence of complex structures, chemistry, and life. The word tuned is where the discomfort begins, because tuning implies a tuner, and physics is not supposed to have those. The constants are what they are. We measure them. We use them. We cannot derive them from any deeper principle. They sit in our equations as inputs, numbers that have to be fed in from experiment because no theory produces them from first principles. What does it mean that the universe's fundamental parameters sit in a narrow range compatible with our existence, and that we have no explanation for why they have the values they do? Most physicists will tell you this is either a selection effect, we can only observe a universe compatible with our existence, or evidence for a multiverse where all values are realized somewhere. I think both of those answers are technically valid and deeply unsatisfying, because neither one explains why these values. They only explain why we see these values. That is a different question. But what if the multiverse is not just an explanation, but the least uncomfortable version of a much stranger set of options? If the constants of physics appear fine-tuned for life, the simplest way to make that seem less remarkable is to multiply universes. If there are infinitely many universes, each with different values of the constants, different strengths of forces, different masses of particles, then somewhere in that infinite collection, a universe like ours will exist. We live in it because we could not live in any other. The fine-tuning dissolves into statistics. This is Leonard Susskind's answer. He is one of the most prominent physicists alive, a founder of string theory, and he has argued seriously that the multiverse is not a speculation, but an implication. That the string theory landscape of 10 to the 500 solutions is not a problem to be solved, but a map of actually existing realities. The argument has a clean logic to it. and it has a serious problem. A theory that explains our universe by proposing infinitely many universes we cannot observe makes no predictions that can be tested against our universe alone. Any value of any constant is compatible with the theory because some universe in the infinite collection will have that value. A theory that is compatible with every possible observation is not doing the work we need a theory to do. Ask yourself what the difference is between an explanation and a story that makes any outcome seem inevitable after the fact. Paul Steinhardt, one of the original architects of cosmic inflation, has turned sharply against the multiverse for exactly this reason. He argues that a theory which cannot be falsified is not science. It is a framework for avoiding questions rather than answering them. And here is where I land on this. The multiverse may be real. The physics pointing toward it is serious, but accepting it as an explanation requires giving up on something that has been the engine of physics since Newton. The idea that reality is specific enough to be wrong about. If every possibility is realized somewhere, we lose the ability to be surprised by what we find. And a physics that cannot be surprised has stopped being physics. To understand why, we have to look at what happens when the theory built to explain all of this produces something even stranger than a multiverse. In 1980, a physicist named Alan Guth proposed that in the first fraction of a second after the Big Bang, we are talking about 10 to the minus 32 seconds. The universe underwent a period of extraordinarily rapid expansion. Not fast, exponentially fast. In an almost immeasurably brief moment, space stretched by a factor of at least 10 to the 26th. Everything we can observe today expanded from a region smaller than a proton. This idea is called cosmic inflation, and it solved three major problems simultaneously. It explained why the universe looks the same in every direction. It explained why space is geometrically flat rather than curved. It explained why we do not see certain exotic particles that earlier theories predicted. Three problems, one mechanism, clean predictions that matched observations. Inflation became the standard picture of the early universe. Then the complications arrived. The same mathematics that makes inflation work also implies that once inflation starts, it does not stop everywhere at once. Different regions of space stop inflating at different times, each becoming a separate bubble universe with its own properties. This is called eternal inflation. And it produces not just many universes, but infinitely many, each potentially with different physical constants. Steinhardt, who helped develop the theory, eventually concluded this was not a feature. He wrote that a theory which predicts every possible universe predicts nothing at all. If inflation can produce any outcome, it cannot be tested against any specific outcome. He called it a serious crisis for the theory. What does it mean when the most successful theory of the early universe leads inevitably to a framework that cannot be tested? And what does it mean that the two most celebrated theoretical frameworks of the last 40 years, string theory and inflation, both lead to the same conclusion? Infinitely many universes, zero experimental access. There is a darker layer here. Fire a single electron at a barrier with two slits cut into it. Behind the barrier, place a detector screen. If the electron is a particle, a tiny ball, it should go through one slit or the other and leave a single mark on the screen. If you fire many electrons, you should get two clusters of marks, one behind each slit. What you get instead is an interference pattern, alternating bands of many marks and no marks spread across the screen. The pattern that light makes when two waves overlap and either reinforce or cancel each other. The electron, fired alone, went through both slits simultaneously. It interfered with itself. It behaved as a wave. Now put a detector at one of the slits to find out which one the electron actually went through. The interference pattern disappears. The moment you measure which path the electron took, it stops taking both paths. The wave collapses. You get two clusters of marks. Particle behavior. The act of looking changed what happened. This is not a quirk of the experimental setup. It is not about the detector disturbing the electron physically. Physicists have run versions of this experiment where the measurement is made by entangling the electron with another particle far away. No physical contact with the electron at all. The interference still disappears. The act of information being available anywhere in the universe about which path the electron took is enough to change the result. So ask yourself what kind of reality this describes. One where what happens depends on whether it is being recorded. One where the electron's path is not determined until the information about it exists somewhere. That is not a metaphor for quantum weirdness. That is a literal description of what the experiment shows. What does it mean that reality behaves differently depending on whether it is observed? And what does it imply about everything that has ever happened with no observer present? To understand why, we have to look at what happens when you push this question further, and ask whether the past itself is fixed before someone looks at it. John Wheeler was one of the physicists who gave black holes their name. He was also responsible for one of the most disorienting thought experiments in the history of physics, and then for watching it become a real experiment that confirmed his intuition. Wheeler proposed this: take the double-slit setup, but add a twist. Do not decide whether to measure which slit the electron went through until after the electron has already passed the barrier. Make the choice, observe or not observe, at the last possible moment, after the electron is already in flight past the slits. Classical intuition says this should not matter. The electron already went through one slit or both. Whatever happened, happened. Your decision now cannot reach back and change it. But quantum mechanics says otherwise. And when the experiment was actually run, using light rather than electrons, with the decision made by a random number generator after the photon had passed the barrier, the result matched quantum mechanics. Choosing to measure which path was taken after the photon had already traveled through the apparatus changed the pattern on the screen, retroactively. The past behavior of the photon depended on a decision made in its future. What does that mean for what the word past actually describes? In quantum mechanics, the past is not fully determined until information about it becomes fixed in the present. The photon did not have a definite path through the slits until the decision about whether to look was made, even if that decision came later. Ask yourself how much of the universe's history is genuinely settled, and ask yourself what it means that the answer might be less than you think. And I think this is the point in the conversation where the word alarming in the title stops being dramatic and starts being precise. This is not philosophy. This is what the experiment shows. The past is not fully real until the present locks it in. But what if the connection between particles makes this even stranger? Because it operates not just through time, but across any distance in space. Take two particles, let them interact so that their properties become linked. Then separate them. Send one to a lab in Paris and one to a lab in Tokyo. Now measure the spin of the particle in Paris. The instant you do, the particle in Tokyo has a definite spin too. Not approximately. Not after a delay for a signal to travel. Instantly, regardless of the distance. This is quantum entanglement, and in 1982, Alain Aspect's team in Paris confirmed it experimentally with enough precision to close the main loopholes that might have allowed a classical explanation. The result has been confirmed many times since. The 2022 Nobel Prize in Physics was awarded specifically for this work to Aspect, John Clauser, and Anton Zeilinger. Einstein called it spooky action at a distance. He meant it as a criticism. It turns out to be an accurate description. The instant correlation is real, but it does not allow you to send a message faster than light. The outcome of each measurement is random, and you cannot control what result you get. So the theory does not violate relativity in a way that allows faster than light communication. But it does mean that two particles, separated by any distance, are not fully independent systems. They share a state. What happens to one is instantaneously correlated with what happens to the other. What does it mean for our picture of space that two objects on opposite sides of the universe can be connected in a way that ignores the distance between them. Space, in the quantum mechanical picture, does not separate things the way we assume it does. The distance between two entangled particles is, in some sense, irrelevant to their physical relationship. And if distance can be irrelevant, what exactly is space doing? Most physicists will tell you entanglement is well understood mathematically. And I think that is true. What is not understood is what it means for the nature of space and locality. And whether the smooth, continuous space of general relativity can survive contact with a quantum reality where distance sometimes means nothing at all. To understand why, we have to look at the most serious attempt to explain all of this without invoking an observer, and what it revealed instead. For decades, the measurement problem sat in physics like a splinter that everyone learned to ignore. Quantum mechanics works. The predictions are right. The question of what actually happens during measurement, why the superposition collapses, why one outcome appears instead of all of them, was treated as philosophical rather than physical. Then, in 1981, a physicist named Wojciech Zurek proposed a framework that seemed, for a moment, like it might dissolve the problem entirely. He called it decoherence. The idea is this: quantum systems do not exist in isolation. An electron in a lab is surrounded by air molecules, photons, vibrations in the equipment. Each of these interactions entangles the electron's quantum state with the environment. The superposition does not disappear, it spreads. It becomes entangled with so many particles in the environment that the different branches of the wave function can no longer interfere with each other. They effectively become separate. The interference pattern is lost not because the wave function collapsed, but because the coherence between branches was washed out by the environment. This is real. It is measurable. It explains why quantum superpositions are fragile and why large objects behave classically. They decohere almost instantaneously because they interact with so many particles. But here is what decoherence does not do. It does not explain why you get one outcome. After decoherence, the mathematics still describes a wave function with multiple branches. One where the particle went left, one where it went right. The branches no longer interfere, but they are all still there, in the mathematics. Decoherence tells you why the branches stop talking to each other. It does not tell you why you end up in one of them. So ask yourself what kind of solution that is. We replaced one open question with a cleaner version of the same open question. And what I find most honest about where this leaves us is this: every serious attempt to explain the foundations of quantum mechanics has either introduced untestable elements, parallel worlds, hidden variables, or left the core question unanswered. We have been working on this for 100 years. The question is not getting smaller. This brings us to something even more fundamental: the question of whether the framework we use to describe quantum reality contains time at all. If you write down the equation that is supposed to describe the quantum state of the entire universe, combining quantum mechanics with general relativity in the most straightforward way, physicists know how. Something strange happens. The equation works, but time disappears from it. This equation is called the Wheeler-DeWitt equation. It was developed in the 1960s by John Wheeler and Bryce DeWitt as one of the first serious attempts to write down quantum gravity. And it has a feature that has bothered physicists ever since. The wave function of the universe that the equation describes does not evolve. There is no time variable. The equation is static. The universe, according to this mathematics, does not change. But the universe does change. You're reading this. Things happen. Sequences of events occur in a definite order. Time is the most immediate feature of experience, the one thing that seems impossible to argue away. And yet, the equation that is supposed to describe reality at its most fundamental level does not contain it. So where does time come from? One answer, developed by physicists Don Page and William Wouters in the 1980s, is that time emerges from entanglement. From the perspective of the universe as a whole, nothing changes. But inside the universe, subsystems become entangled with each other. And from the perspective of one subsystem looking at another, change appears. Time is not a feature of reality at the fundamental level. It is what entanglement looks like from the inside. Ask yourself what it means to be inside a process that produces the experience of time without time being a fundamental ingredient. Ask yourself what it means that the most basic feature of your experience, the fact that one moment follows another, may not be written into the deepest laws of physics. And ask yourself whether a universe described by a timeless equation is the kind of universe you thought you were living in. To understand why, we have to look at the physicist who spent his life on this question, and what the effort cost him. Ludwig Boltzmann was one of the greatest physicists of the 19th century. He built the mathematical foundation connecting the behavior of individual atoms to the large-scale properties of heat and gas. The framework he developed, statistical mechanics, is still in use today, unchanged in its essential structure. And the central question of his life was one that the framework raised but could not answer. The laws of physics are symmetric in time. Run any fundamental physical interaction backward, and you get an interaction that is equally valid. A ball bouncing off a wall runs the same way in either direction. Two particles colliding and exchanging energy look the same forward and backward. At the level of fundamental physics, past and future are interchangeable. But in practice, time has a direction. Heat flows from hot objects to cold ones, never the reverse. Broken glasses do not reassemble. Eggs do not unscramble. The past is different from the future in every observable way. This is the second law of thermodynamics. Entropy, the measure of disorder, always increases. Time runs in the direction of increasing entropy. Boltzmann understood this statistically. A hot object placed in a cold room cools down not because the laws of physics require it, but because the number of ways the energy can be distributed unevenly is vastly smaller than the number of ways it can spread out. Moving toward equilibrium is overwhelmingly more probable. Time's arrow is a statistical effect, but this explanation has a problem. It requires that the universe start in an extraordinarily low entropy state, highly ordered, very improbable. Why did it start that way? Boltzmann spent years on this question and could not answer it. His colleagues attacked his work. His mental state deteriorated under the pressure. He took his own life in 1906, with the question unresolved. It is still unresolved. We still do not know why the universe began in a low entropy state. We still do not know why time has a direction at the fundamental level. The statistical explanation works beautifully once you accept the initial condition. Nobody can explain the initial condition. But what if time is not just directionless at the fundamental level, but altogether absent? An illusion generated by something deeper. Carlo Rovelli is one of the most serious physicists working on quantum gravity today. He is also the person who has most directly argued, in technical papers and in public, that time as we experience it does not exist at the fundamental level of reality. Not that time is weird, not that time is relative, that the flow of time, the sense of a present moment moving from past to future, is generated by our particular position inside a physical process, and that the universe itself has no such arrow built into it. The argument builds on three pieces. First, the Wheeler-DeWitt equation. The universe's wave function is timeless. Second, Boltzmann's statistical mechanics. The direction of time is a thermodynamic effect of entropy increasing. Third, thermal time. The sense of time flowing is generated by the way a warm system, like a human brain, interacts with its environment. We are not observers of time. We are products of entropy. Think about what that means practically. The feeling that now is special, that this moment exists and others do not, is, in Rovelli's framework, a feature of being a warm, entangled system embedded in an environment. From outside the system, there is no now. There is a static structure in which all moments exist equally, and the experience of moving through them is generated by the entanglement between the observer and the world. This is not mysticism. Rovelli is doing physics. The framework produces mathematical predictions. And it fits with what the Wheeler-DeWitt equation already suggests. That time is not a fundamental ingredient of reality, but something that emerges from it. So ask yourself what you are. If the experience of moving through time is a thermal effect generated by your own entropy, ask yourself what the word now means if no moment is more real than any other. And ask yourself whether a universe without a fundamental present is the universe you have been living in all along, and you simply never had a way to see it. To understand why, we have to look at one last piece of the puzzle, the tiny asymmetry that explains why we exist at all. In the beginning, physics says, the universe produced matter and antimatter in equal amounts. For every proton created, an antiproton. For every electron, a positron. Matter and antimatter annihilate each other on contact. They convert entirely into energy and vanish. If the universe began with perfectly equal amounts of both, everything should have annihilated. The universe should be empty. Pure radiation, no structure, no atoms, no stars, no us. The universe is not empty. Something tipped the balance. For every billion antiprotons produced in the early universe, there were 1,000,000,001 protons. When the annihilation was over, 1 proton per billion pairs survived. That tiny excess, 1 part in a billion, is everything. Every atom in your body, every star in the sky. The entire observable universe is made of the leftovers from an asymmetry so small, it barely existed. In 1964, James Cronin and Val Fitch were running an experiment with particles called kaons. They found that kaons did not behave identically to their antimatter counterparts in certain decay processes. The laws of physics were not perfectly symmetric between matter and antimatter. This asymmetry is called CP violation. Cronin and Fitch won the Nobel Prize in 1980. The discovered asymmetry is real, but here is the problem. The amount of CP violation measured in particle physics experiments is far too small to account for the matter-antimatter imbalance we observe in the universe. The known sources of CP violation could not have produced the surplus of 1 part in a billion that allowed matter to survive. Something else contributed. We do not know what. Ask yourself what it means that we owe our existence to a physical asymmetry we have measured, confirmed, and still cannot fully explain. We are here because the universe broke its own symmetry by a tiny fraction. We cannot account for the full size of the break. And what I find genuinely vertiginous about this is that the question of why we exist at all, not philosophically but physically, remains open. We know the mechanism. We cannot explain the magnitude. We are here because of an anomaly we do not fully understand. This brings us to the final act, where the mathematics of physics stops describing our universe and starts describing all possible ones. The landscape of string theory contains 10 to the power of 500 solutions. Each solution is a valid set of physics, different particle masses, different force strengths, different constants, different laws. Each one describes a universe that could exist. Only one of them is ours, and we have no way to determine which one or to derive our universe's properties from any deeper principle. To understand what 10 to the 500 means, consider this. The number of atoms in the observable universe is estimated at 10 to the 80. The landscape of string theory contains more possible universes than there are atoms in our universe, raised to the power of 6. It is not a large number in the ordinary sense. It is a number that makes the concept of largeness meaningless. Leonard Susskind, who has thought about this longer than almost anyone, argues that the landscape is real, that all these solutions are physically instantiated as actual universes in an eternally inflating multiverse. We live in one that happens to support our existence. The other 10 to the 500 are out there, somewhere, with laws of physics that would not support anything like us. But here is what this framework cannot do. It cannot tell you why the constants of our universe have the specific values they have. It cannot derive the mass of the electron, It cannot calculate the strength of gravity. It can only say, some universe in the landscape has these values, and we observe them because we are in that universe. So ask yourself whether that is a theory of reality or a theory of all possible realities that happens to include ours. Ask yourself whether the difference matters. And ask yourself what physics becomes when its deepest framework describes everything, and therefore, in a precise sense, predicts nothing specific. And here is what I think this moment in physics actually represents. We built tools precise enough to reach the foundations, and found that the foundations are not a single bedrock, but an ocean of possibilities with no bottom we can stand on. To understand why, we have to look at what happens when you follow this logic to its endpoint, and ask whether reality and mathematics are the same thing. Nick Bostrom is a philosopher at Oxford. Max Tegmark is a physicist at MIT. They arrived at similar places from completely different directions. Bostrom through the logic of computing and probability, Tegmark through the mathematics of physics, and the place they arrived at is genuinely difficult to dismiss. Not because it is comfortable, but because the objections to it turn out to be harder to make than they look. Tegmark's argument starts with a question. What is the difference between a mathematical structure and a physical reality? When physicists describe the universe, they write equations. The equations have solutions. Those solutions describe particles, fields, space-time, forces. We say the equations describe reality, but Tegmark asks, what would it mean for the equations to be reality? For the mathematical structure to be physically instantiated, not because something outside it makes it real, but simply because the structure exists mathematically. If every mathematical structure that is consistent is real somewhere, then the universe is not a physical thing described by mathematics. It is a mathematical thing that happens to include observers like us who experience it as physical. Bostrom arrives from a different angle. If civilizations can run detailed simulations of reality, and if many such simulations can be run, then the number of simulated realities will eventually vastly outnumber base realities. If you are a conscious observer in any reality, the probability that you are in the base reality rather than a simulation approaches zero. Ask yourself how you would test either of these proposals. You would look for anomalies, places where the simulation cuts corners, where the resolution of reality breaks down at small scales, the Planck length, the quantization of space-time, the discrete structure that loop quantum gravity predicts. And here is what I find impossible to dismiss about this. We already know that reality is digital at some level. Energy is quantized, spin is discrete, the universe comes in packets. Whether that is a sign of underlying mathematics or underlying computation, or simply the nature of quantum mechanics, the structure of reality looks less like a continuous physical substance, and more like information processed according to rules. But what if the most unsettling thing is not whether we are in a simulation, but that we cannot tell the difference, and that the physics we have built is equally valid in both cases? There is a final layer here. Niels Bohr was the architect of the Copenhagen interpretation, the framework that told physicists not to ask what quantum mechanics means, only how to use it. He was right that the framework works. He was possibly right that certain questions about it cannot be answered. And he articulated something called the principle of complementarity that cuts to the heart of what physics is doing when it describes reality. The principle says this: an electron is not a particle, it is not a wave. It is something for which we have no word and no image. Something that behaves as a particle in particle experiments and as a wave in wave experiments, and whose nature cannot be captured by either description alone. The two descriptions are mutually exclusive and simultaneously necessary. You cannot observe both aspects at once, but you need both to say anything complete about the electron. Bohr extended this beyond electrons. He argued that complementarity is a feature of reality at the quantum level, that reality does not have single, exhaustive descriptions. It has multiple descriptions that are each correct in their domain and incompatible across domains. What does it mean for a science built on finding the one true description of reality to arrive at the conclusion that no single description is complete? Because that is what complementarity implies. The wave description is correct. The particle description is correct. They cannot be merged into a single picture. Reality accommodates both without being reducible to either. And this is not a temporary situation, not a gap waiting to be filled by a deeper theory. Bohr argued, and the mathematics supports, that this is the structure of things. Most physicists accept complementarity as a feature of quantum mechanics without dwelling on what it means for the project of physics itself. And I think that is worth dwelling on. We set out to describe reality with a single, consistent framework. We found instead that reality requires multiple frameworks, that these frameworks are incompatible, and that each one is indispensable. That is not failure, but it is not what we were looking for. And what it implies when you put it together with everything else we have covered is something that physics has never quite said out loud in a single sentence. Let us try to say it now. Start with 4%. That is the number. 4% of the universe is described by the best physics we have. The rest, dark matter, dark energy, whatever lies beyond the standard model, sits outside our framework, acknowledged and uncharacterized. We know it is there because of what it does. We do not know what it is. Now add what we covered. 2 foundational laws that are individually perfect and mutually incompatible. A measurement problem that has been open for 100 years. A procedure at the heart of our most accurate theory that the man who built it described as sweeping infinities under a rug. A multiverse of 10 to the 500 solutions with no principle to select ours. A past that is not fixed until the present locks it in. A universe whose deepest equation contains no time. Constants tuned to permit our existence with no explanation for the tuning. An asymmetry we owe our existence to that we cannot fully account for. 2 descriptions of the electron that are both correct and cannot be reconciled. This is not a list of unsolved puzzles at the edges of a complete theory. This is the center of physics. These are not footnotes. They are the main text. And I want to be clear about something, because this is the part that I think matters most. None of this means physics has failed. Physics has done something harder than succeeding. It has been precise enough to map exactly where its own understanding ends. It has built instruments sensitive enough to reach the boundaries of what can be known and describe them in exact mathematical language. That is not failure. That is the most honest thing a science has ever done. But here is what it means for you. Sitting here, in a universe built from the 4% we understand. The floor you are standing on, the air you are breathing, the light you are seeing, all of it is part of the 4%. The rest is present everywhere around you, in every cubic centimeter of space, in every galaxy you will never visit, threading through everything that has ever existed. And we have no idea what it is. Ask yourself what it means to live inside a reality that is mostly unknown. Ask yourself whether the silence around this fact is comfort or avoidance. And ask yourself whether knowing the shape of what we do not know, mapping the exact outline of the dark, is enough to count as understanding. I do not think it is, but I think it is the most important thing physics has ever produced, not the answers, the precise, unignorable shape of the questions.